99.
Okay, so
Right.
yeah, so all good things must come to an end. That Amber's out and I'm back in. So
For more good things to come.
well, okay. So that means the numerical linear algebra part is finished. Although linear algebra will still play a bit of role in what's to come. Okay. One thing I want to get on the record while being recorded. What?
8 classes.
Yeah. So, because we have 5 homeworks altogether, and as well as the final, which is a choice between an oral final like last semester or a program project. The assignment for a coding part, I actually need to get that posted because I have it ready somewhere. So I can put that up soon. So like the next couple of days, I'll have it up by Wednesday, so you can look at that. Now the thing is, that's on the very last topics we're going to cover. The oral final is like last semester, where you choose one of the major areas of a course. So in this case, there's going to be ODEs, time-stepping methods for ODEs, solving system linear equations, so Amber's whole part, that's another major topic area. And then what I'm going to do today, is systems of nonlinear equations and boundary value problems. But boundary value problems is what the coding option is on. And then for a final, you can also choose the breadth option, where it's questions that are less in depth, but they cover everything. So you're basically asking for a comprehensive final. But like I said, it's depth versus breadth. So
What's all
your
on
choice.
ODE time stepping? What's it up to?
One step and
Like one-step methods, like run-cutter methods, multi-step methods, stability, consistency, stability, everything that I covered before Amber took over. So.
Girl, we like that down on the script.
Oh yeah, it's true.
Yeah, so
Oh yeah, we.
I'm leaning towards that.
Okay.
option, maybe.
Okay, so then before Amber, so you Adams Martin, Adams Bashford, all
Right.
that before the Gaussian elimination, LU, all that started.
Right.
So then linear systems, so direct and iterative are that.
That's one part. Yeah.
Oh.
Yeah. So those.
So now the stuff we did for homework 4, is also part of that
Yes.
second
It is.
depth.
Yes.
That's big depth. Everything
That's a
Amber's
big depth.
Yeah, and then everything else, even though it doesn't all go together, but since in terms of time, it's basically the last third of a course, roughly, even though it's actually a little less than that, which is kind of nice. Yes, so systems of nonlinear equations, which I start today, and boundary value problems, that's the last major topic area. Okay. So as we get closer to the end, you can let me know what you'd like to do. At least there's fewer of you than last semester, so scheduling is going to be easier. Plus, I'm not traveling, sadly.
So are we going to do this the week before or the week of finals?
Either or, yeah. At least I'll be around during finals week, so we can be fit in then, like Monday through Thursday. Okay, and then the other announcement I want to make is I will drop the lowest homework. So there's only 4 that you need to turn in. So, okay. Actually, that applies in all my classes, by the way. I mean, the same announcement's coming in 606. So you only have to do 6 out of the 7 homeworks for that. Okay. Yeah. So I guess a few people in the room are excited about that. Okay. All right, so I have to remember to post the coding option by Wednesday. Okay. Also, I will do my best. I know I'm behind on grading, and we're all behind.
Yeah.
Let's face it. So I don't feel as bad. So I'll be getting something graded back this week. I'm not sure if it'll be this class or my other class, or preferably both. But I will do my best to make steady progress on that between now and the end of the semester. Okay, so now we can get into the next segment of the course. actually built on material that was covered last semester, 465-60, about solving a single nonlinear equation. But I had to wait this long to get to systems because to generalize from a single equation to system of equations, we need some linear algebra tools, and now we have them. But it's been a while. It's been like last September when these things were covered, and I know not everybody even took that class. So I'm going to do a brief review. Okay. So what we saw last semester, you were trying to solve a single nonlinear equation that can be written in the form f of x equals 0. So you get it in that form. And there were certain methods that were covered last semester. First is bisection, a very reliable method. All you needed to know was that there was a sign change within an interval, and you were guaranteed to obtain an approximate solution, but it's slow. Also, so that was one big knock about against bisection that I gave last semester, how slow it is compared to other methods. There's another big knock against bisection, and that is, unlike other methods, it doesn't really generalize very well to systems of nonlinear equations. It's basically a one-dimensional method, so for functions of a single variable. So in fact, we're not even going to talk about it for systems. Second method, which does generalize systems, and I'll be spending time on today, is fixed point iteration. And I'll give a quick rundown about the most important aspects of that. So you rewrite the equation in this form, x equals g of x. So that way you can obtain the solution by successive substitution. So the idea is you choose initial guess, and then you get each new guess by plugging the old one into your function g. And there are many ways you can take f of x equals 0 and transform it into x equals g of x, some more straightforward than others. But one thing that was important then, and it's going to be important again today, is how do you know that this iteration is going to converge for a given g? So a key property, you need g to be a contraction, which is like the real analysis or functional analysis term for it. So we need g prime to be less or equal to some constant rho that is less than 1. Okay, so sorry, it converges if. So this is a sufficient condition for convergence, assuming that a fixed point even exists, which there's conditions for that too. But this is the main thing we want to focus on. We needed this to be true to be guaranteed a convergence, and when we go to systems of equations, we're going to have a similar condition to this, where instead of dealing with g prime of x, you're going to be dealing with a matrix, and instead of absolute values, you're going to be dealing with norms, or spectral radius. So all those properties that Amber covered, we're going to need for this. Okay, and then third approach, Newton's method, the fastest of the ones that we covered. Okay, so this uses a tangent line approximation of f to approximate the solution. So your formula is xn plus 1 is equal to xn minus f over f prime. Basically, it's computing the x-intercept of a tangent line at xn. So it converges very rapidly, but it's unreliable. If you don't have a good initial guess, it might converge slowly, or actually might fail to converge at all. Now, in one variable, you have a tangent line. For a function of two variables, you have a tangent plane. More generally, you have a tangent space. So this method does generalize to higher dimensions, but instead of dividing by a derivative, we'll be inverting a matrix. So linear algebra tools are going to be needed again. On Wednesday is when I'm going to cover this. And finally, because Newton's method requires a derivative, so that's an extra cost. So fix of Newton's method is a secant method. So that replaces the tangent line with a secant line, whichever method gets its name. It slows down convergence somewhat, but it's still quite fast. And a lot of people still prefer secant method over Newton's method because it's a trade-off. It doesn't converge as fast, but
Doesn't compute the derivative.
yeah, so the work per iteration, so more iterations, but not many more, and less work per iteration.
Isn't this the one that starts with 2?
Yes, yeah, it needs 2 initial guesses. And usually what you can do is if you have a good initial guess that you might use for Newton's method, you can maybe perturb it a little bit to get a second guess. And we're not, so the secant method, like Newton's method, does generalize to higher dimensions. So on next Monday, I'm going to discuss what are called quasi-Newton methods, and one in particular called Broyden's method. That is an attempt to make Newton's method more efficient. Okay. Because the linear algebra involved can be very expensive. Okay, so everything here except bisection has a natural generalization to systems of nonlinear equations. All right, so today the focus will be on fixed point iteration. Okay. Right. Now, first I need to get across some notation about, first of all, what do I mean by a system of nonlinear equations? So what kind of equation are we actually going to try to solve? And second, since we're going to design iterative methods like these, where you take an initial guess that's now a vector quantity, and we want that to converge to a solution of the system, what does it mean when we have several variables and we're trying to get a sequence of iterates to converge, when each iterate is a vector? Okay.
Can you put those vectors in a matrix?
What?
Can you put all those vectors in a matrix? Or?
Well, matrices will come about dealing with derivatives and so forth. Yeah. Okay. So before I can talk about solution methods, we need a clear statement of a problem. Okay. So we're going to solve a system of n nonlinear equations. So we have n functions of each one a function of n variables set equal to 0. So it's like our f of x equals 0 now n-fold. So f1 is equal to 0, f2 all the way down to fn. But we still have the same number of inputs and outputs. So n input variables and output variables. Now for convenience, we can express all of these in vector form. So we have a vector valued function, big F, of vector x must be equal to the 0 vector. So this vector x has all the components, all of our n independent variables, and big F of x is a vector that has our component functions f1 of x, f2 of x, fn of x. Okay. All right. So f1, f2, etc. These are called component functions, also known as coordinate functions. Okay. All right. Now, we need some notion of convergence. For functions of n variables. Okay. So the idea is, when I say the limit as a vector x approaches some vector x naught of a vector valued function f of x. Okay, because the idea is we're going to have sequences of iterates that are hopefully converging to a limit. So the limit L also is a vector. So we just define this convergence on a component-wise basis. So we need to have all of the component functions converging to the corresponding component of your limit. Okay. Now, what about the fact that here we have a vector x approaching a vector x naught? So we can say that, so some of you may recall seeing this from like real analysis, or if you haven't taken it, you will see it there. So for any epsilon greater than 0, there exists a delta greater than 0, such that if the vector magnitude x minus x naught is less than delta, and to use a notation that Amber introduced for vector norms, we're taking 2 norm in this case, so this is just Euclidean distance. So if x is sufficiently close to x naught, then each component function of x is within epsilon of the appropriate component of the limit. But you have all these limits existing, all n of them, simultaneously. Okay, so this is a rigorous definition of a vector valued function of n variables having a vector quantity as the limit. Okay. Now, we also need a notion of continuity. So a vector valued function f is continuous at a given point in n-dimensional space x naught. And now that we know what a limit means in n dimensions, that if the limit approaches the function value, then the function is continuous there. So straightforward generalization of a definition of continuity for a function of a single variable. And some of you I heard may have forgotten or never seen the corresponding one-dimensional definitions. But in any case, I figure a refresher is always good.
Remember, these are big F's, right?
Yeah. Yes. Everything here Well, unless there's a subscript, then are referring to a component function.
Right.
But these should be vectors. These are vector value functions. Okay. All right. Now, okay. So now what I'm going to do is I'm going to describe how you would solve a system of equations like this one using fixed point iteration. And in fact, you've already seen an example of fixed point iteration actually for a linear equation. So I'll make that connection for you. Okay. And as far as, we actually will get to an example of system of equations. I try to present fixed point iteration. Okay. So you start with your given system of nonlinear equations, so n equations and n unknowns to solve, and you rewrite it in this form: x is equal to some other vector value function g of x. Basically, you're rearranging algebraically the equations to isolate your unknowns. I just said you don't have values for those unknowns yet. And now, how you rearrange in a way that you get an effective iteration, I'll show you when we get to an example some guidelines for doing that. Okay. Now, for the algorithm, what you do is you choose some initial guess, I'll call it x naught. And then your algorithm is very simple, actually. You keep plugging in your previous iterates into G, and you get your next, whoops, that's xk, not x0. Okay. And then your next guess comes out, you keep plugging it in, keep iterating like that, keep plugging in the old to get out the new, and so forth. And then you check for convergence. So for instance, check if some norm of xk plus 1 minus xk is less than some tolerance. That would be a good way to check for convergence, for instance. So you have some if statement there. And if that test for convergence is satisfied, then you're done. Your iteration is complete and you have an approximate solution. You should also have some sort of maximum number of iterations imposed, because what if the iteration is not converging? And you want your code to bail out. Next week, so next Wednesday, the 20th, yeah, that's the day I was looking for, is we'll have that's when our next lab is, and we'll talk about these methods.
Why do you use superscripts instead of set? Like what?
To avoid ambiguity, because a lot of times when you're doing vectors, subscripts used to refer to a component of a vector. Yeah. Okay. All right. Now.
The superscripts are the iterate numbers, right?
Exactly. Yeah. Okay. Now, we need some conditions for convergence of this iteration. Okay. So first, we'll talk about existence. How do you know the function g actually has, actually, a lot of terminology I used last semester you may not remember. I'll try to refresh on that. So when does a function such as g have a fixed point, which I'll call, using similar notation to last semester, x star. So fixed point satisfies equation x equals g of x. So in other words, it is a solution of your system of equations. So given a function g, how do you know it even has a fixed point? So a fixed point exists if g maps some domain D into itself. Last semester we needed a function little g to map an interval AB into itself. So that concept of existence of a fixed point generalizes to higher dimensions. So if you can identify some domain D, this time a subset of Rn, for which this works, then you know at least a fixed point exists. Okay. Now, what about uniqueness? Okay. So x star is a unique fixed point of G in your domain D if you have this condition satisfied. The Jacobian matrix of G, and now that's an n by n matrix. So the norm of this matrix must be bounded by some constant rho that is less than 1 on this domain D. So if you can establish that this condition holds, then you know that not only is there a fixed point, but it's unique. And if that condition is satisfied, you also know, this is similar to the one-dimensional case, fixed point iteration is guaranteed to converge as long as your initial guess, so for any initial guess in that domain where this condition holds, convergence is guaranteed.
When you say unique, do you mean for that equation or for the vector? So you're saying like is any component in x they're already different for the vector of x or just for that equation with no other solution?
So the vector x star is the only solution of this equation.
So it's the entire vector.
The entire vector.
Okay.
Yeah. Yeah. So this anything I stated here holds for all components.
Okay.
Yeah. All right. Now. Okay. And I should mention here any natural matrix norm, like the P norms, like the matrix 1 norm, 2 norm, infinity norm, any of those norms. Whoops. If that condition holds, that is sufficient for convergence. Okay. Now I should mention a stronger condition that's also harder to satisfy. That's a spectral radius of a Jacobian matrix is less than 1. Similar to what we saw with stationary iterative methods. So if you can establish that, because that's harder to satisfy than this. Because you get a situation where a norm of a matrix is less than 1, but the spectral radius could still be, well, actually, sorry, I had that backwards. I mean, this is still a harder condition to satisfy because having the norm being bounded away from 1, being less than 1, that is sufficient for convergence. It is not necessary. Whereas from this, you get basically like a necessary and sufficient iterate condition for convergence. Because you can have a situation where the spectral radius is less than 1, but certain norms might still be greater than or equal to 1. But if that happens, you're still going to get convergence. All right. Now, so I want to show first an example. I'm going to relate this fixed point iteration to what you saw earlier with stationary iterative methods, because those basically are a fixed point iteration, except that's for a system of linear equations rather than nonlinear. And then we'll take a look at an example involving nonlinear equations. Okay. So for general system of linear equations, AX equals B, so the iteration had this form: m xk plus 1 is equal to n xk plus b, where a is equal to m minus n. But I could also write it in this form: xk plus 1, because I can multiply both sides by m inverse, so I get m inverse nxk plus b. So if you want, you can think of this as your function g for fixed point iteration. This is a linear function. So that means that the Jacobian of g is just whatever's multiplying xk. It's just this matrix, m inverse n. That means that the condition for convergence of this particular fixed point iteration is that the norm of m inverse n, well, preferably is well, actually, in this case, I can say less than 1 because it is a constant matrix. But when we have a Jacobian being a function of x, we don't want it to be just less than 1. We want it to be less than or equal to a constant row less than 1. It sounds like they're the same thing, but really they're not. Because we don't want a situation where this Jacobian can get arbitrarily close to 1 somewhere in the domain. Like you might have a limit approaching 1, because then you might have non-convergence. But since this Jacobian is constant everywhere, then having it less than 1 is enough. Now this is a sufficient condition for convergence, whereas a necessary sufficient condition for convergence of this particular fixed point iteration is that the spectral radius of m inverse n is less than 1. And I know that Amber covered this condition with you guys. So like I said, you may have a situation where the spectral radius is less than 1, but a norm of this matrix might be greater or equal to 1, and that's okay, it's still going to converge. But a lot of times showing that the norm is less than 1 is easier, because certain norms, like a 1 norm or the infinity norm, are very easy to compute compared to computing eigenvalues. Okay, so all the theory that Amber covered with stationary iterative methods of what it took to get it to converge is entirely consistent with what I just laid out for fixed point iteration for more general kind of equations, systems of linear or nonlinear equations. Okay. So now what we're going to do is we're going to look at an example of solving a system of nonlinear equations by fixed point iteration. And we can see what are things that can go wrong in trying to assure convergence.
Can you just attach our notes?
Well, they have a notes anyway. Okay, so those of you watching, something went wrong, recording stopped, and missed the entire example. The example is the same one, it's in the notes, covered the end of section 881. So I'm going to angle the board here to what I still have. Okay, so this is the same example at the end of 8.1 where I'm solving the equation x2 is equal to x1 squared, x1 squared plus x2 squared is equal to 1, and trying fixed point iteration, I convert that system to this. So this is my g of x. The notes, there are 2 attempts, and I had those on the board, but one, the recording has been lost. So we write it this way and look at the Jacobian matrix. The spectral radius of a Jacobian matrix is less than 1 near the fixed point, so the iteration converges, albeit slowly. Whereas in the previous version, that's more straightforward, that x2 equals x1 squared, and x1 is the square root of 1 minus x2 squared. Fails because the Jacobian matrix at the fixed point, spectral radius, is greater than 1. So that is what I was discussing, that's the key difference. So what happens is, an implementation detail, if we implement the second set of equations this way, is a Jacobi-like approach where we use x1k and x2k wherever we have new information or not, or we can always use the latest information available about x1, about prior components. So I use this down here. That's kind of like Gauss-Seidel. And what we were just observing is that actually simplifies to this equation. So I basically have a different g. Sorry, please bear with me. I hear the sound of packing up, and it's extremely annoying. So what we have is x2 k plus 1 is equal to x2k, and then x1 k plus 1 is equal to square root of x2k. So now it's like we have a new g that does not involve x1 at all, which is kind of interesting. So the Jacobian matrix of this g, I better angle this without shutting it off. So there's no dependence on x1, so that column of Jacobian is 0. And then we have this derivatives. And then we have minus x2 over square root of 1 minus x. Oh, actually, we just have, 1 over 2. Okay, so that's your Jacobian in that case because there's no squaring going on. So in fact, this is going to have a
Spectral radius.
yeah, it's going to have a spectral radius less than 1, I'm pretty sure.
Yeah.
Because, so 1/4, so 1/2. Yeah, so the spectral radius is, I believe, it's going to be less than 1/2. We'll try this in lab next week and see if it converges faster than the other one. Okay, so sorry about the mix-up, those of you watching with the video, but it's all in the example. I did not add in anything new to that except what you've seen here. So I will try to be more careful about it, or I might re-record it later after all of you are gone.
But we can definitely show that the one norm would be less than 1, right?
Yeah. So actually, it's really the norm. Sorry. Not the spectral radius. Spectral radius would have to be done differently. But the norm should be like a 1 norm. Should be less than 1/2. Okay. I put question mark because I'm doing this in a rush, but I'm pretty sure that's actually the case. Okay. Yeah, because well, we'll have to check that. Okay. All right. God, I hate when that happens. Okay. I'm going as you guys leave, I'm going to move this computer just so people watching can get a better look at the screen. Okay, but they can pause it so you can walk in front. Go ahead, get out. Okay, I'm making this, now that the students have gone, I'm making this brief addendum to the discussion I was, about the example because some of it was lost. Sorry about that, I'm not sure what happened. So, okay, so this is the example that's at the end of section 8.8.1, solving a system of equations. There are many ways, we need to write this in the form x equals g of x for vector valued function g. That means isolating variables, like we isolate x1 in one equation, x2 in the other equation. This is an effective way to do that, just rearranging the first equation and then also the second equation to isolate x1 and x2 respectively. So this is in the form x equals g of x, where this is a choice of g of x. A bad choice, which is discussed in the notes, is x 1 is the square root of 1 minus x2 squared, and x2 is equal to x1 squared. So we didn't really do anything to the to this equation that describes a parabola. And I had this graph earlier. This is a parabola that describes the second equation. First equation is just a unit circle. And we see that there are two solutions. And this is the one that we're focusing on. And we can see that, based from the graphs, that if I define the domain D, the square, x between 0 and 1, that means that whatever fixed point iteration function I choose, either of these two choices, G maps that domain D into itself, which implies that a fixed point exists. Okay, so in theory, fixed point iteration gives us that. So we have this good choice here and a bad choice here. This one was examined first. We see that the Jacobi matrix definitely has a norm greater than 1 on much of the domain. Also, near a fixed point, the Jacobi matrix has a spectral radius greater than 1 for this set of equations. I just repeated it down here. Whereas for this choice, the good choice, the spectral radius is less than 1. And as far as understanding, trying to get the spectral radius, it's not something that's easy to do when you have functions of x1 and x2. But I was just pointing out, for these kind of matrices, the Jacobi matrices in both cases have this kind of structure. 0 entries in the diagonal, whatever entries on the off diagonal. And from that, the trace is 0, the determinant is just alpha times beta, so the eigenvalues are complex conjugates of one another. So this is what they are in this second case. But that's still difficult to judge whether it's less than 1 or not, but at least we know we can determine numerically what the spectral radius is. So it's less than 1 for this choice, greater than 1 for the earlier choice. And by earlier, I mean earlier in the notes. And the other thing I want to point out that wasn't really discussed much in the notes is, when you make this bad choice, it seems like the most more straightforward one, and we find that derivatives are too large. The way to fix that is to invert the equations, because from this tip from last semester, if x equals g of x fails, we just reverse the relationship. We work with the inverse function. And that worked well here. We took this equation and we reversed it. We inverted it to get x1 is square root of x2 as opposed to x2 equals x. Sorry. That x1 equals square root of x2 as opposed to x2 equals x1 squared. Equivalent equations, but this one has a smaller derivative, and that's why it works well. And then we just fix the other equation accordingly so that we isolate x1 and x2. So that tip from the single variable case of inverting a relationship between variables works just as well in higher dimensions as it does in one dimension, even if it's done just one variable at a time. So the note says a Jacobian matrix from the first case. Here we have a Jacobian matrix for the second case, so we can examine them and get an idea as to why fixed point iteration fails in one case and converges in the other case. We will look at this example with regard to fixed point iteration in a lab next Wednesday, and we'll take a look at this situation where we can tweak. Sorry again. Apparently, every time I move a computer, the recording stops. So the last thing I was going to say was, we're going to look at this situation in the lab where we tweak the iteration using Jacobian-like approach in this case on the left, and or the Gauss-Seidel-like approach on the right. And we seem to get a smaller spectral radius, but we will have to analyze this further because I didn't really not something that we can really be sure about without plugging in values and so forth or doing more algebra. So this is what we will get back to next Wednesday, the 20th. So we'll cover on Newton-like methods next time. Sorry about the recording mix-up. I'll be more careful about when I move the computer and make sure recording doesn't stop. So again, sorry about that.